Okay, you're on.
Oh, good afternoon, everybody, and welcome to SETI Live. We are broadcasting from various places today, and I'd like to introduce my colleagues and companions today. We are going to be talking about citizen science discoveries, exoplanets and asteroids. So joining us from Lausanne in Switzerland, we have Julian de Lambailly, an amateur astronomer and citizen scientist. And joining us from somewhere en route 5 in California, he refused to give us an exact location, is Dr. Frank Marchis. He is the senior planetary astronomer at the SETI Institute. And of course, as always, in SETI Live, we would love you to write in, tell us where you're listening and watching from. And if you have any questions, do write them in. And Rebecca is here to transfer those questions to the speakers today. So I'm going to start off with Frank, because these observations and this citizen science project is using an instrument called an Evascope, which is a special type of telescope. And I was wondering if you could tell us a little bit about the Evascope and what does make that special.
Good afternoon, Simon. Yes, so the Evascope stands for the Enhanced Vision Telescope. It's a telescope that we created several years ago. The company called Unistellar. So the Evascope, it's a small telescope that you can carry around. It's a digital smart robotic telescope that basically will allow you to enjoy the dark sky from your house, from your backyard, and also conduct scientific investigation. It's a small telescope, so you can it's basically, it doesn't look such a big deal, but it is equipped with a CMOS detector. It has a smart computer on board, and you can use it even if you don't know much about astronomy. It basically will tell you what kind of object you can observe this night when you set it up, and you can select the target. It will point toward the target, give you information about the target, and you can enjoy the dark sky, see nebulae, galaxies, and comets.
Okay, I'm going to bring up a picture of this is Julian, I think, if everyone can see that, with his Evascope, and you can see it's quite a small size telescope, and certainly one of the problems of observing faint objects, especially in urban areas where there's so much light pollution, is you really do not get a good image. The background noise is too high. The telescope doesn't integrate unless you have a camera attached. But this allows you to look at very faint objects and record those images directly, doesn't it?
Yeah, that's correct. So this telescope, because it's integrated light, it can basically allow you to see very faint objects up to magnitude demonstrated 17. And we think we can even go deeper in some very dark sky area. And because you have a good sensitivity and you have a good stability of the system, we were expecting to be able to do great science with this network of telescopes. So that's the reason, basically, in 2017, we connected this project, the Unistellar project, with the SETI Institute.
Right. We've got lots of people listening in already from Louisiana, from Switzerland. They haven't said where, so they may be just down the street from you. Mississippi, Italy, Austria, Norway, Portugal, India, Prague, and Spain. So welcome everybody from around the world. So Frank, say a little bit more about the connection with the SETI Institute and this project.
So the SETI Institute is the scientific institution of the project in the US. Scientists of the SETI Institute work with Unistellar, and we develop scientific programs. So scientific programs are basically, right now we're in a pilot phase, but scientific program consists in sending alerts to our users. So any Evascope citizen astronomer can receive an alert by email at the moment, but soon on the app directly. And they can conduct observation that we think to be useful for scientific observations. So, for instance, we can send alerts in case there is an asteroid passing by nearby Earth, and our users will be able to collect the data. This is part of the planetary defense program. But we also have alerts related to transiting exoplanets So Jupiter-sized exoplanets transiting their stars. We can detect these transits, and also alerts related to occultations. And so in this case, it's basically an asteroid passing between us and the star, and the star will disappear for a few seconds, and the unistellar Evascope citizen astronomer located on the band of visibility will be able to see this event and record the data for us. So SETI Institute's researcher collect the data, make first the announcement, send the notification to the users, collect the data, the users will send to us, do the data processing, and send to our users, astronomers, the information about the status of the observation, if they were successful or not, and what was discovered, what's been done. And then this data also stored into a professional astronomer database. It could be AVSO, as it can be Euraster. So those are basically repositories where scientists look for scientifically useful data for scientific research.
Okay. Now, of course, citizen science, amateur astronomers have a long, long history. William Herschel was a citizen scientist and went on to discover a planet. And Julian, so you join a long list of famous names who have got excited by the sky and by astronomy. What got you interested in astronomy in the first place?
When I was a child, my parents, they just bought me a book. This was a book about solar system. And I was 8, and I wanted to know everything about the stars and the planets. And they bought me more books about the stars and the cosmos. And I saw all those images from the Voyagers program, from Saturn and every big planets, and I just became a fan. And I think I'm an astronomer since that time. And at 12, I got my first telescope, and so I could observe Saturn, its ring, for the first time, and just make a big wow. Just like everyone is making a wow the first time you see with your own eye.
When you see Saturn the first time,
when you see Saturn,
yeah.
Something you remember all your life.
Yeah.
And it doesn't matter if you're 8, 15, 60, everyone's makes the same wow.
Yeah.
So this is very, very long passion I have. And I wanted to be an astrophysicist at that time. While I didn't do the study in that direction, and so it just remained a very strong passion to me. And in my 20s, I wanted to see more, so I had a small telescope, 4-inch, 4.5-inch, just like the Evascope, but without all the technology involved in. And I wanted to see galaxies and nebulas, and so I bought a bigger, a Dobson 300 millimeters. And this was another wow effect when I could see the galaxies and the nebulas. But there was always that problem with the light pollution. So I always had to take my telescope out in the mountain. And when you on the top in the top of a mountain, and in January it's minus 15, well, you're alone up there.
Yes.
So I missed something. I missed a way to share my passion with my friends, family, and everyone. So I used to organize nights of observation. Sometimes I take my scope in my garden, backyard garden, and I just invite the neighbors to come and to see whatever I can show them. And this is something I like to do. And then I wanted to see something more. So I was used to observe the object with my naked eye on my scope, and this is only gray images, and I wanted to see the color. but I wasn't very interested in astrophotography, because astrophotography is it's a hard discipline. You really need a lot of material, and there is a lot of process you have to learn. There is a learning curve, very steep learning curve to do astrophotography, and I wanted to see live view. And I remember that time I was thinking, I need a scope that could accumulate the lights, and I could show in, and this way I could see in the how do you say oculaire?
Yes, the eyepiece.
The eyepiece, yes, thank you. In the eyepiece, and see every colorful images you used to see in the magazines. And so that was the time I was looking for a system, for technology to do this, and it was many years ago. And I bought another telescope. It was still a Dobson but with motorized Dobson and with a camera. So this way I could finally observe images in color, in a colorful way, from home, from the city. But this wasn't enough. I was alone. I couldn't share what I was doing, and I couldn't participate and be part of a scientist's study or scientist work, observation campaign. So the day I heard the Evascope was something real. Maybe it was 4 years ago. I don't remember, 4 or 5 years ago, but very, very soon. I think a year or year and a half before they made the Kickstarter campaign. I was following their job, and I said, yes, they are doing just right what I need. My dream is getting real. And so I joined the campaign, the Kickstarter campaign, very quickly. And I was backer number 23 over, I don't remember, more than 2,000 people just backed it. And then I had to wait for the Evascope to come to me. And it came, finally came this year.
So, and you've done some amazing things. We're going to hear about your observations in a second about Qatar 1b. I just want to say that we have a lot of people, and I can't remember where the list I left it, but people from Cornwall in the UK, Canada, Arkansas, Minnesota, Texas, Philadelphia, Germany, Argentina, San Francisco, Utah, the Netherlands, Brazil, North Carolina. Frank tells us he is in Coalinga, California, so that's great. We can know where to come and rescue you now that we've got a location. And Iraq, so this really is a global audience watching, which is very exciting.
Nice.
So Julian, you were part of the observing campaign, and you looked at this exoplanet, Qatar 1b. Can you say a little bit, first of all, about the observations and about what you discovered? And we'll put up the light curve in a minute that you can talk through.
Well, the observation, how did I do it? So as soon as I got my Evascope, I wanted to see an exoplanet. So this was a dream. This was a dream to detect an exoplanet, and seeing it was a possibility with the Evascope, I had to do it, and I had to do it quick. And I found someone who was working with Frank, Dan Peluso, who is a PhD student in astrophysics, and he's working actually on detecting exoplanet with the Evascope. And so I asked him for help, and he gave me any information I needed to do the observation. So I needed the targets. I didn't know how to choose the target. I didn't know how to set the Evascope outside and how to make it work to see something like this. And he gave me any information I needed, and I am very grateful. Thank you, Dan, if you hear me. And so I only had to to take my Evascope on my garden. I live in a city, so there is a lot of light pollution, and this is a big problem. But with the Evascope, we can do many, many things, even in the middle of a city. So this is really, really, really impressive. And so I took it outside an hour before observation. So I turn it on. I do the automatic field recognition. So this is quite impressive how the Evascope does it at 10 to 20 seconds only. And I know with my other telescope how long it can be with other systems, but with the Evascope, it's really, really pinpoint done in really, really easily done. So you
and
take it out.
This is how it looks at the sky. You're setting up so it knows exactly where it's pointing in the sky.
So you take it out and you just press a button and he knows at what star he's looking. And now you say, I want to go there or there or there. And there is a list of objects. You can go and you can enter manually enter coordinates. And so I had to manually enter coordinates. And I had a sky chart to help me just to check if the coordinates were right, which were right, and I can tell the Evascope is really, really precisely motorized because every time it just go to the right position, and this is something I've never achieved with another system. And so this is something really very well made, and it makes that scope really easy to use to anyone, really. So this is very, very impressive. So I pointed the right coordinates, and then I had to set observation parameters. So it's about gain, exposure time, which Dan Peruso told me how to do it. And I started recorded for little longer than 3 hours, but with only 30 minutes sessions, because in every 30-minute session, I had to check if the star was still in the field of view of the Evascope. And actually, it was the case. Within every 30 minutes windows, I could see the stars. And at the end of the observation, then I have to download. So all the frames. The thing is, the telescope was taking a photograph of the star every 4 seconds with a 4-second exposure time. And so all that frames are stored in the Evascope. And then I have to download it to my phone. And from my phone, I can upload all the data to Unistellar servers. And from there, my job is done. And there are the real scientists getting in action and analyzing the data and producing, finally producing the light curve you see. We will see maybe. And that was work of Thomas Posito. So thanks to him as well. And they provided me that light curve, and I remember a few weeks ago when they told me, yes, you've got a positive observation, and I was just like, woo! I just got my first exoplanet, and it was with that telescope and so easily done from my backyard garden in a city. It's something I couldn't imagine a few years ago, really.
Something
so
amazing.
I'm very proud of it.
So this star you're looking at is about 600 light years away, I believe, and the planet itself is sort of a Jupiter-type planet. And this, as you see on the screen now, I'd like you to talk us through this. This is what's called a light curve. And so what this has been produced by is you taking a succession of photographs of this star, and what you're getting, you can see that the data points, which are scattered around quite a lot, but when you average out those data points, you get this red line, which is the average of all those data points. What is this showing here as we look at this red line?
I can answer to that if you want, but Julian.
Yes.
Okay. Okay. Yeah, go ahead, Frank.
You'll do better.
Yeah.
So what you see here is basically the attenuation of light of the star due to the fact that the planet is passing between us and the host star.
Mm-hmm.
So it's a very dim attenuation of 1% only. And this is due to the fact that basically the planet, which is a Jupiter-sized planet, is occulting the star. So from this, you get three main information. One, you know that there is a planet around the star. That's one information. Katana 1b has been detected in 2010, and has been observed regularly, so we knew it existed. And as I said, this is a pilot program, so we were trying first to see if it's possible to do it. So we use a planet which is known. So Katana 1b is one of those. From the depth of the attenuation, knowing the size of the star, you can infer the size of the planet. So from this, we basically get a depth which is in agreement with the observation, because that's what we're expecting for a planet which is roughly the size of Jupiter. And then from the attenuation as well, we can get the timing. The timing is basically when this event is occurring. And the timing is extremely accurate in the case of this observation. We get an timing which is an accuracy on the timing which is less than 5 minutes. So it means that we are able to derive precisely when this event is happening. And this has a huge interest for astronomers, because we know there is planets around us, exoplanets in orbit around other stars, and now we're starting observing them. And the more regularly we observe them, the better we refine the orbit of those planets. So by knowing accurately the orbit of a planet, you can basically predict more accurately when this planet will be in 5-10 years, when instruments like JWST, Ariel, ABEX, all these gigantic space telescopes will be online. It will be possible to observe this planet with an extremely accurate timing, knowing exactly when you have to point JWST to Katana 1 to observe the transit, for instance.
So you're laying the groundwork for these big telescopes in the future, basically.
Exactly.
Yeah.
And it's basically what we have done in planetary science in the past, when we have been observing asteroids on a regular basis to derive the orbit of asteroids. So now we have the orbit of 750,000 asteroids. Mm-hmm. So we're going to be doing the same for exoplanets. With this kind of work, we can basically derive the orbit of a large number of exoplanets. Mm-hmm. Mm-hmm. And also, so from the timing, we can also see maybe some perturbation in the timing. And this is happening if there is another planet in the system, like a super Earth inside, or a perturbator like Uranus or Neptune-like exoplanets. So from the perturbation of the timing, we can also detect multiple systems. We can also infer if there is something even more interesting in the system. That's not the case for this one, because that's a hot Jupiter, so it's very close to its star. Mm-hmm. But in the future, we will be able to do the same kind of analysis for a more distant Jupiter, like the one which orbits around the star in a year, 2 or 3 years. And we will be able to derive the exact timing of the event, and maybe detect the presence of Earth-like exoplanet or super Earth.
Right. And this, of course, this concept has a long history, because that's how Neptune was discovered, by looking at the perturbations in the orbit of Uranus. So it's very, very exciting that the same techniques, gravitational interactions between planets that's being used now has been used for hundreds of years. So that's very exciting. We've got a few more people listening in, and then we've got a couple of questions. And then, Frank, maybe we'll turn our attention to the occultation observations. We've got people from Devon, Surrey, Wales, North Georgia, US, Chile, Greece, Portugal, and New Zealand are listening in as well. So welcome everybody. A question, this is probably for Frank from Bonnie. Are the Starlink satellites affecting observations of exoplanets or asteroids? Are they getting in the way of things?
Can you repeat the question, sorry?
Yes, the Starlink satellites that SpaceX are launching, is this a problem for you as an astronomer?
We cannot yet say whether or not it will be a problem, because the final brightness of those is not yet fully defined, because the SpaceX is working in reducing their brightness.
Mm-hmm.
Their number could be a problem on the fact that they will be passing in our field of view on a regular basis. We are working on the way to assess how we could basically remove them on the image. We could remove them numerically, or we could also kind of calculate in real time the orbit of each of them. And one is passing in the field of view, we can stop the integration. That's something we are also studying. So there will be a way to go around this, we hope. It's true that it's making our lives slightly more difficult, but I don't think there is. It's impossible to find a quick solution to that.
Right. Yeah. Yeah. The less things in the way and the less light in the atmosphere, the better for astronomy, I think. But
yeah.
Yeah. Okay, Frank. This was the observations with the Evascope. We've got another very exciting observation. That was the occultation of asteroid 2000 UD52. I'm going to bring up the video now, and maybe you can talk through it and tell us about that observation. If I can find the share screen button. Yeah, here we go.
So this is one of the another scientific case we have been working on with Unistellar. In this case, as I mentioned briefly before, we want to detect indirectly the presence of an asteroid by observing a star and observing basically the star disappearing at a specific time. So this happened like 4.
Is this showing up? I just want to make sure that this is showing up on the screen.
Please.
It is good, perfect. And it's very short, so I'm repeating it.
Yes, you have to repeat it manually a lot. So we started this program in February 2020, and one event was happening above France. It was crossing all the way from Normandy to the Pyrenees, close to Toulouse. It was basically what we call that's what we call the visibility band. So any observer located in this area, with a tiny band of 10 kilometers, would have been able to see the star disappearing for a few seconds, or less than 2 seconds. We noticed that we had a bunch of citizen astronomers located in this area, so we asked them to observe it, and 6 of them did the observation, especially exactly at the right time that we specified based on our calculation. And one of them, Moran Studer, sent us his observation, and we detected this occultation from his observation. He lives in Normandy, in the north of France, and he basically saw with his Evascope the disappearance of this 11 magnitude star, as you can see. And this event lasted extremely short, less than 1 second, 0.3 seconds to be accurate. Those kind of occultation are interesting because they give us information about the asteroid itself. Because we know exactly where is the star, so because of the observation, because of the disappearance of the star, we know exactly where is the asteroid at the specific time. So that's one information. To give us an idea, because of the duration of the event, of the size of the asteroid. The bigger is the asteroid, the longer will last the occultation. And if we have multiple observers, we see basically the shadow of the asteroid on the surface of Earth. So that gives us an idea of the shape of the asteroid. And finally, the more exciting part in my case, because that's what I've been working on for the past 20 years, if you look the occultation, you'll be able also maybe to see the presence of a moon or rings around asteroids, because people don't know that, but a significant number of asteroids have moons or rings. And this is one of the ways we can detect them, by observing an occultation. If you have a moon, you will not see one occultation, you may be able to see 2 of them. one by the moon, and then one by the primary, the main body of the system.
Okay. We have a question from. Yeah, sorry, carry on, Frank.
No, so from this occultation, this is the first positive one. I should mention that we have done a lot of them, and we have a large number of observers who have been trying to observe them, and this is the first positive one. But we should mention that a negative one is also interesting because it gives us an idea where the asteroid was not, for instance. So that also helps us to refine the orbit of the asteroid later on.
Right.
We have done roughly 18 occultations since February 2020, involving 30 people. So that's significant. Yeah. And for this one, we have detected the occultation. We know the occultation is rough. The duration of the occultation is in a rough agreement to what we expected, of course, knowing the size of the asteroid. Okay.
Fascinating stuff. I know we're coming up to time now, and I want to hear a little bit about what's in the future for the Evascope and what's coming up next in terms of campaigns. But first of all, Julian, what's next for you? What are you looking forward to observing in the sky now? Are there any projects that you would like to become involved with, or are you an exoplanet man from now on?
Yeah. From now on, I'm an exoplanet man, and I keep trying to detect. So I had five tries now. I tried 5 times, I mean, and I'll keep it because yeah, I just think it's so fascinating, and I always try to participate the occultation, asteroid occultation campaign. So I did twice already with negative results, but they are results. And I like it. So it's quite it's easy to do. It doesn't take a lot of time. I mean, compared to the exoplanets transit observation, it's 2, 3, 4, 5 hours observation. An asteroid is like you have to observe for 10, 5, 15, 20 minutes maximum. So it's really easily done. And because of the small size of the telescope, you have it in the backpack, pack it in the car, and you can go a few kilometers away, maybe 100 kilometers away, just to get on the path of the asteroids. And so I'm really interested in this campaign as well.
Okay, cool. You can read more about these particular discoveries on our website, on the SETI Institute website. Rebecca will also put a link up to Unistellar's website that will give you more information about upcoming campaigns. So Frank, just to round off, tell us what's next. What is Unistellar and what's the Evascope's doing next?
So next for us is to make it easier for people to do scientific investigation using the Evascope. So as I mentioned, the telescope is controlled with an app. So we are working in making easier for people to select the targets and to observe the target. The reason we are doing this is because we're partnering with a program called the Exoplanet Watch, led by JPL. And the Exoplanet Watch is basically a program to confirm exoplanets detected by TESS, the NASA's mission that which is observing the whole sky and searching for exoplanets. So TESS was launched roughly 2 years ago now, and TESS already discovered 1,835 TOI, target of interest, so potential exoplanets. So what they need to go from TOI to planets is to have additional observation taken by another network. So the exoplanet, the unistellar SETI network will be able to do this. In fact, we calculated that 10% of those TOIs are observable with the unistellar network at the moment. So that's 180 candidates. That's a lot of targets. That's a lot of observation that we can collect with our Evascope network. Yeah. So that's the first step. In the field of occultation, we have launched this month the Asteroid Month. So if you go on our website in unistellaroptics.com, you will see that we have selected already some occultation which are visible in the US and in Europe. We have specifically one involving the asteroid Pallas, number 2, and one involving the asteroid Ares above the US. So those are easy occultation, and that will be very interesting to train observers to learn how to do occultation, for example. We will continue this. We have set up a partnership as well with different groups at the Observatoire de Paris and also at SWIRI to do occultations involving trans-Neptunian objects and Trojan asteroids, which are significantly more difficult because the orbit of those bodies is not as well known as for main belts. So we need a large number of stations across a very wide area of the world to be able to see those occultations. So that's the future. The future is also to increase the network. Yeah. And the network will increase very soon because we are in the process of shipping units in the US and in Europe, but also we're expanding to Japan, Australia, New Zealand, Hong Kong, and Singapore at the moment. So hopefully there will be more stations everywhere in the world in the next 5-10 years.
Excellent. Well, thank you very much. There's lots of exciting things to look forward to, and we'll obviously be following up on that on the SETI Institute website, and probably have more SETI lives to talk about new discoveries. Julian, thank you very much for joining us from Europe and from Switzerland. That's wonderful. Frank, thank you very much for the update on this. Thank you to everybody for watching. So from me, Simon Steele at the SETI Institute, and from Julian and Frank, enjoy the rest of your day and speak to you soon. Bye-bye.
Thank you.
Bye-bye.
Bye-bye. Have a good